Okay. Welcome to our New Discoveries lecture series. I'm Ramon Aerosmith. I'm the Associate Director for the School of Earth and Space Exploration, and I want to thank everyone for coming out tonight. This is the last of our New Discoveries lectures for the semester. It's been a great season, and I don't know if you saw as things are flashing there, we got a good program coming for the fall. So I'll talk a little bit more about that at the end. And so I'm going to introduce Professor Ariel Anbar in a couple minutes. He's the main attraction. But before we get started, I want to take a moment to thank Susie Marston and other friends at CC for helping make tonight's event possible. We're in the Marston Exploration Theater. And also we have a teaser video from ASU's Knowledge Enterprise Development of the latest KED talk, just released today. Featuring CC's director, Lindy Elkins-Tanton. So be sure you can find the whole video at home. But let's watch for a couple minutes here.
So why do we explore space? First of all, because exploration is a human imperative. It's built into us. Everything from Magellan to Captain Janeway. And exploration aligns humankind looking outward instead of allowing us to be distracted by the irritations that lie between us, both as people and as nations.
Quite short. I thought it might be a minute longer. There's a lot more. I watched the whole 8 minutes earlier today. It's really nice. Check it out. Okay, so coming to the main event. So Professor Ariel Anbar is a scientist and educator interested in Earth's past and future evolution on an inhabited world and the prospects for life beyond. His group's major focus is the chemical evolution of the atmosphere and oceans as revealed by the development of novel geochemical methods. He earned his undergraduate degree at Harvard University, then he went on to get his master's and PhD at Caltech. And he was part of a really well-known laboratory called the Wasserberg Laboratory, and very famous, and many influential people, including Ariel, have come from there. He was trained as both a geologist and a chemist, and he's a president's professor here at ASU. He's on the faculty of both the School of Earth and Space Exploration and the School of Molecular Sciences, so that's chemistry, as well as a distinguished sustainability scholar on the Global Institute for Sustainability. And most recently, he's become the director for the Center of Education Through Exploration, which is a new activity here at ASU that's oriented towards transforming learning through exploration of the unknown. And it's really exciting. It's something he's really passionate about. And so want to acknowledge him for that. So tonight's talk, however, is going to explore how our understanding of the past, present, past, and future of life on Earth shapes the search for life beyond. So let's welcome Ariel Anbar.
Thank you. Thanks. Is this working? Can you hear me? Hear me in the back? Okay. So thank you. That was a wonderful introduction. The one thing you left out is that So I worked in the Wasserberg lab as a graduate student. It's a very famous lab, but we never referred to ourselves, nor on the publications are we referred to as the Wasserberg lab. We referred to as the lunatic asylum for interesting reasons. So hopefully that actually won't be reflected in the talk here, but you can be the judge later on. So I also want to thank you for the introduction in general, and I want to put a shout out to all my colleagues in CC and the students and the entire CC community to thank all of you guys for making this such a fantastic place to work. I've been here 12 years now, and the honeymoon just kind of keeps coming. It's always a fun place to be. So we're going to talk today about astrobiology. We're going to talk about the search for life beyond Earth. But we're going to do that by showing you some of the connections between Earth sciences and space sciences. Earlier today, I was talking to Professor Hartman, who gave one of these talks a month ago, and she said, be sure to tell them what you want to talk about. So slide 2 is really what I want to talk about. So this is the School of Earth and Space Exploration. Earth and space, what do these actually have to do with each other? Right? Many of these talks, especially I gather the more popular ones, are space-related. And what I hope you get out of this talk is how the study of the Earth both today and in the past, and our concerns about Earth's future really animate and drive and inform our research into the prospects for life beyond Earth and whether or not there is life beyond Earth. These things are intimately related, and I hope that comes across by the end of the talk. So we're going to begin with motivations. Before we talk about how we look for life beyond Earth and what are the possibilities, it's probably worth talking about why we bother with this search at all. Science is a human endeavor, and humans are motivated by all sorts of things. And so it's important for us to understand our motivations, understand why we do what we do. Why do we look up at the sky and wonder whether or not we're alone? And for me, this picture, this photograph, this beautiful photograph recently taken from the Cassini spacecraft at Saturn really encapsulates and motivates the way I think about this. So this is Saturn. You can see here, this is the planet. Here's the rings. And here is this little pale blue dot. That's us. This is a self-portrait. Right? Literally, it's a self-portrait. You're there. You're in that picture. All of you are in that picture. Right? You are here. Now, this picture was organized by Carolyn Porco, who's a brilliant planetary scientist who's heavily involved in the Cassini mission. And it's really a retake of a very classic photo that some of you may have seen, the famous pale blue dot photo that Carl Sagan ensured that the Voyager spacecraft would take, a picture looking at Earth from the outer solar system. And I want to read you what Carl Sagan wrote I got to find my notes here, get away from messages. I want to read you just a passage from his Pale Blue Dot book describing his thoughts when he looks at this image, because they're very evocative and they help frame why we do what we do. And I don't sound like Carl Sagan, but I'll do the best I can here. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there. The Earth is a very small stage in a vast cosmic arena. When I look at that pale blue dot image, and when I think about Carl Sagan's words, and realize that all of human history is in that dot, I can't help but think about the fact that humanity's future is also in that dot, and wonder what is the future of that pale blue dot. And when you look at that pale blue dot a little closer, you see something remarkable, especially if you look at the night side of the Earth. You see that this planet is being transformed. It's being transformed by us. Humanity is becoming a very powerful force on the face of the Earth. We worry about it in terms of climate change, but it's pervasive in all sorts of ways. We are becoming one of the most important parts of the Earth system in many ways. And geologists even have a name for this. We call this the Anthropocene, the age of humans. So welcome to the Anthropocene. That's where we are. And the future of this planet is going to be shaped very much by us. I'm not going to show a lot of data here, but I want to show one chart, which to me I think embodies a lot of what motivates the search for life beyond. It actually has to do with thinking about our future on this world. This is a chart of world energy use. So here's exajoules, units of energy. Here's time from 1750 into the future. Here we are now. Here's global photosynthesis. This is the energy used by the biosphere. Right? A lot of energy, right? All the plants capturing all the sunlight that they capture, doing everything that they do, and then all the animals that eat those plants. That's the energy flow that is being captured by the biosphere. This is us. This is what we're doing. Started very low, it's increasing, and these numbers are pretty solid. This is following an exponential kind of curve. We can extrapolate it forward. What I want you to see here is already today, we're at about, if you look at the numbers, we're at about 10% of the global biosphere. In other words, we are capturing and utilizing energy at a scale that already starts to be comparable to what nature over 4 billion years of evolution has produced. We usually think about that in terms of CO2 being emitted into the environment or something like that, right? The negative stuff that we do like that. And that's worth worrying about. But forget about CO2 for a minute. Let's say all our energy use came from things that weren't fossil fuels. This is energy that's being used to do stuff on the face of the planet, to move things around, to build things, to do all the good things we do and all the bad things we do. There's no way that we can utilize that much energy relative to the natural biosphere and not have an impact on the face of the planet. There's just no way. It doesn't matter what energy source there is. We are transforming the world. That's simply the way it is. It's an evolution. You can think about it as an evolutionary transition. Just like once upon a time, biology figured out how to make use of sunlight for energy, we have evolved this ability to use tools to capture energy and do even more. And that's a biological innovation. It's a transition that's happened and it's not going to go back. This curve, extrapolating forward is always a risky business. I wouldn't put too much stock in exactly how this curve works, but it's going to keep increasing. And notice that if you do take stock in this, it's only about 100 years from now before we are actually literally rivaling the global biosphere in the amount of energy that we utilize and manipulate. That's going to leave a mark. So the future, the real question we have about our future is, well, what are we going to do with all that energy that we're using? What kind of mark are we going to leave? Right? Are we going to be able to handle this? Or maybe not. Maybe we won't be able to handle it. Maybe we'll go extinct, like so many species have gone extinct before on this planet. Maybe we'll handle it in a way that's perhaps not all that graceful. Our science fiction fan, you might recognize this photo. This is Coruscant, the capital of the old Republic in Star Wars, which is actually echoing a theme from Isaac Asimov of Trantor, of this totally urbanized world. A pale blue dot that becomes a sort of gray and brownish dot because it's covered by steel and concrete. Maybe that's our future. Maybe our future is something a little more in between, a sort of high-tech future in which we find a harmonious balance between the pre-existing natural world and the natural world as we remake it with technology to do the various things that we want to do to improve our lives and the lives of those we love. Maybe that's our future. We don't know. We don't know what our future is. So we look at that dot, and it's if you start thinking about our future in this way, it's hard not to then start to wonder, well, are we the first ones to go through this? Is this the first planet to deal with this? Is this the only planet to deal with this? Is there a multitude of civilizations out there that have already gone through this? Is there a galactic civilization out there that we're just waiting to join if we can just figure it out? Or are we absolutely unique in the cosmos? Are we the only ones figuring it out? It's sort of like entering adolescence, right? I have a teenager who fortunately isn't here, so I can say this, right? So teenagers go through all this existential angst. Why am I here? What am I doing? And it's always then one of the first things you think about when talking to a teenager is role models, right? Examples of others who have gone through this before, right? So if we knew that there was one advanced civilization out there that just existed, right? That had gone through what we've gone through and had mastered it successfully, that would transform the way we think about it, right? That would transform the way we think about our future. So for me, that's the motivation. I want to know if we're alone because I want to know if what we're about to go through, what we're dealing with now, this evolutionary transition of life on the planet to this technologized form of life, technologically mediated form of life. How does this work? And is it a transition that we are going to successfully cope with or not? It would be wonderful to be able to know that. And so we ask, are we alone? Now, other people may have other motivations. Motivations are intrinsically personal, but those are the thoughts that I have that lead me to be interested in this question. Now, we have to be a little cautious. It's all well and good to think about your motivations and why you're doing things, and they tend to be emotional and passionate. If they aren't emotional and passionate, you probably should find something else to do. But you have to be careful if you're going to be a scientist because you don't want your emotions and passions and desires to be shaping what you want to find out. We don't want the search for life beyond Earth to turn into a quest for a holy grail, a kind of almost quasi-religious thing where there's this thing out there that we're hoping to find, and if we find it, we've made it. And if we don't, we're crushed, right? We don't want that to be the nature of this search for life. And we know we don't want that because we've been fooled before. The problem here is that if you allow your biases to get in the way, then you fool yourself. And as the famous Richard Feynman said, the first principle in science is that you must not fool yourself. And you are the easiest one to fool. And in astrobiology, in the search for life beyond Earth, we've suffered from this in the past. And the most classic example is embodied here in these pictures. This is Mars. This is actual photographs of Mars here. And these are interpretive drawings of Mars made by astronomers 100 and 150 years ago. looking through the earliest telescopes, trying to figure out what's on the surface of Mars. The most famous of these astronomers was Percival Lowell, for whom the Lowell Observatory is named. Not a slouch. Came out to Arizona, built that observatory, which eventually led to the discovery of Pluto and many other things. But he looked through these early telescopes, and he convinced himself that he saw, and others did as well, canals. Canals that Percival Lowell was convinced were artificial constructs made by an advanced civilization living on Mars, that he hypothesized was coping with dramatic climate change. Climate change is a theme that seems to come up quite a bit. This was 100 years ago. Was coping with dramatic climate change. Their planet was drying up and was building massive waterworks to move water around the planet. And it was very influential. A lot of people believed this. But it was a mirage. He was seeing real features, but distorted. You can see there's some correspondence to these real features of these canals. He and other astronomers were seeing real features, but obscured by the poor quality of the optics of the time. And then their minds would play tricks on them. They would see what they wanted to see. So we need to avoid that. As much as many of us want to believe that there is life out there, an advanced life out there even, we need to be very careful and be our own worst critics. We need to be very skeptical and act like scientists, not like true believers, when we actually engage in this quest. So we have a science that we've developed and defined around the search for life beyond Earth. And the science is called astrobiology. That's the name of the field. It's a new field. The word astrobiology, I've tried to figure this out, where it came from. The oldest reference I can find is in a Star Trek episode, actually. Astrobiologist Lindstrom is recommended by the M5 computer to accompany the landing party to beam down on a planet. It's the first reference I can find to astrobiology. So if you're a Star Trek fan, pat yourself on the back. It anticipated the future. But the word became popular in the mid-1990s when Dan Goldin, the NASA administrator at the time, decided to essentially create this as a field and poured a lot of money into it. So astrobiology, a field of science, is the study of the origin, evolution, distribution, and future of life in the universe. When you frame it that way, it doesn't matter whether there is a teeming galactic civilization out there or if we're the only life in the universe. Either way, we want to know about the origin of that life, whether it's all over the place or just here, how it evolves, how it's distributed, and its future. And that's as important if we're alone as it is if life is ubiquitous in the universe. Either way, we want to know, we want to study it. That's the science. To put it in sort of historical terms, which are kind of fun to think about, what we're doing in astrobiology is we're exploring a hypothesis. We're exploring this hypothesis that the Copernican revolution applies to biology. Let me tell you what I mean by that here. So many of you probably know that once upon a time, we used to think that everything revolved around us. Some of us still do, but literally, scientists, we thought that everything revolved around us. So this is best embodied by Ptolemy's astronomy, 2nd century astronomer, who refined what we call the geocentric view of the universe that had Earth at the center and everything revolving around it. The moon, the sun, all the planets, all the stars, everything revolved around Earth. The Earth was at the center of creation. And this was a bit of a complex model because once you start really making detailed astronomical observations, you realize that it doesn't really work all that well unless you start imagining that some of these other planetary bodies are in their own little spherical, what are called epicycles and stuff like that. So this was a complex model when the people really got into it. But this was the prevailing view for quite a long time. And it wasn't until quite a bit later, the 16th century, where Copernicus advanced this alternative view, a view that was heliocentric, sun-centered. It put the sun at the center of the solar system. It put the Earth as a planet going around the sun and the other planets going around the sun. And in many ways, this simplified the interpretation of the observations, and as we know now, this is correct. This is the Copernican revolution. It was the start of a whole series of insights that, in physics and chemistry, that showed us that the Earth, or convinced us that the Earth is a typical place in the universe. So not only was the Earth not at the center of the solar system, it's just one of many planets going around the sun, one of 8 or 9, depending on how you want to count them, planets going around the sun. Turns out the sun is not really the center of anything. It's kind of off in the galactic suburbs. And our galaxy is really not in the center of anything. It's one of 100 billion galaxies in the observable universe. And so the trend of science has been to increasingly show that we are typical in the universe, and hence that the laws of physics and chemistry that we observe here can be generalized elsewhere. And this is the Copernican revolution. And we presume that since biology is a manifestation of chemistry and physics, that this will also apply to biology. We presume that in biology also, it will turn out that the Earth is a typical place, and hence that life will be ubiquitous. It makes sense. It's a very logical argument. I buy it. It's very reasonable. But it's a hypothesis. Until you actually find life elsewhere, you don't really know if it's true. It may be that the origin of life is a fantastically complicated and unlikely thing. It may be that the origin of life is easy, but the evolution of multicellular organisms is a rare and complicated thing. Or that the evolution of intelligence is rare and complicated. We don't know, right? And the only way we're going to really figure this out is by looking around and seeing what else is out there. So we're testing the hypothesis that the Earth is a typical place in the cosmos, which is the Copernican insight. So as I said at the outset, we're focused here on the Earth in this talk. Not focused on the Earth, but I want to show you how Earth science is key to addressing these kind of questions. So I've already tried to show you that, at least for me, it's the study of the Earth and concerns about the Earth that motivate the search for life. What does the Earth actually tell us in terms of informing that search? Well, one thing it tells us is that indeed there is observational data we can make on Earth that is consistent with the Copernican idea. He wasn't thinking about life, but with the idea that the Earth is a typical place. So this is, this looks nondescript and weird probably to most of you. This is a very close-up view of a kind of rock formation called a stromatolite from a place called North Pole in Western Australia. Don't let the name fool you. North Pole is a fiendishly hot place. The Australians have a cheeky sense of humor, and so they called it North Pole. And what you're seeing here, these laminations that you see here are widely accepted by those who study these things very, very closely and intensely as evidence of life at about this should actually say 3.5, my apologies, at about but there may be other signs of life as early as 3.8 billion years ago. These rocks are from 3.5 billion years ago. GA is geological jargon for billions of years ago. The Earth is 4.6 billion years old. Today is up here. So the earliest signs of life that we have on Earth are around here. So we think these were microbial mats living in a shallow ocean that get kind of crinkled up, and the textures are very indicative of that kind of thing. They're old and they've been beaten up, and so you can argue about it, and people have, but the consensus is that indeed these are ancient stromatolites. So so the Earth is about 4.6 billion years old, and by 3.8 billion years, we have some evidence of life. By 3.5, you have this stuff that's quite convincing to people who study this sort of thing. So what that tells us is that life seems to have gotten going on Earth pretty quickly, fairly quickly in geologic terms. And arguably, we argue quite a lot about how habitable the Earth was during this time. You know, it may have been impossible for this kind of life to really emerge until not that long before 3.8 billion years ago. And so the general sense is, when you look at Earth history, is that life got going pretty fast, right? Which would make sense if the Earth is kind of a typical place, and the rules of biology and chemistry are such that life is not a difficult, unlikely, or exceptional thing. It kind of emerges from the planet when the conditions are right, and the right conditions are not anything uncommon or odd. Life gets going pretty fast. So that's one insight that comes from Earth science. Now, there are going to be a whole bunch of other ones, and I kind of like to show this. This is at the Heart of Astrobiology. Well, let's see what's really important, based on what a bunch of graduate students over the last decade put together, which is called the Astrobiology Primer. So a bunch of graduate students new to the field decided to put together a little booklet that embodies everything that a new graduate student needs to know to sort of get up to speed quickly in the field of searching for life beyond this world. And so at one point, the lead editor of this took that whole document and put it through an analysis of what's called a word cloud. Does everybody kind of know what a word cloud is? A word cloud is where you make a diagram where you rank all the words basically by their frequency of appearance in the document, and the ones that appear the most you print the biggest, and the ones that appear the least often you print the smallest. So the word cloud for the Astrobiology Primer looks like this. So life, obviously, is a word that appears quite a lot in that primer. But the other word that appears a lot is Earth, right? Because the reality is you simply cannot engage this question of searching for life beyond Earth without a lot of information coming from this place and understanding it in a fairly deep way. And it's kind of interesting when you go to astrobiology meetings, you find a heck of a lot of the people there are geologists. In fact, when this field started, and I went to my dean at the time, not at ASU, and I said, this is my field, I'm doing astrobiology. He said, wait a minute, you're a geologist. You're not an astronomer and you're not a biologist. How can you possibly have anything to do with the study of astrobiology? But in fact, Earth is central. So let's talk. So what I'm going to do here is give you a couple of examples, 3 examples really of that. I've already given you a few, but let's go through 2 in some detail and then 1 to sort of wrap up. So one thing we learned from the study of Earth and life on Earth, and this has been a revolution in our understanding over the last 30 or 40 years, is that life tolerates amazing extremes. We don't tolerate extremes all that much. It gets a little chilly, we put on a jacket. It gets a little hot, we strip down to our shorts. And then that's it. Our range of temperatures that we cope with is not all that extreme. But if you go to someplace like Yellowstone and look at the boiling hot springs of Yellowstone, you find that just outside of where these things are boiling, as soon as you get away from the boiling zone, you have microbes living in these kind of environments. You have microbes living in environments that are incredibly acidic. You have microbes living in environments that are incredibly basic, microbes living in environments that are incredibly salty, and so on and so forth. And we didn't know this until really the last generation. We've really learned that life tolerates amazing extremes, and that's expanded our thinking about where life could be out there in the universe. We've discovered at the depths of the oceans life living in places that are cold and dark, life that would be just fine if everything that we know about at the surface pretty much wasn't there, as long as you had an ocean, and in some cases not even an ocean. You just need rock and a little bit of water deep enough. You have microbes that can survive in these very challenging to us, amazingly inhospitable environments to us. There are microbes living deep in the Earth's crust, in little cracks and crevices. So pretty much everywhere you go on Earth, as long as you don't get above a boiling point, you will find microbes making a living. So this has transformed the way, and it continues to transform the way we think about searching for life beyond Earth. So let's take a look at in our solar system. So here's, not to scale, right? The planets are not this close. Unless you're in a J.J. Abrams movie, then you can go from Earth to Vulcan in 5 minutes, apparently. But otherwise, planets are really not this close. So, of course, a lot of searching for life, a lot of the effort around search for life in the solar system is focused around Mars. I assume there was a talk in this series about Mars, and if there isn't, there will be next year, I'm sure. So you're going to hear a lot about Mars, so I'm not going to talk about Mars at all, right? The search for life on Mars, I will say this, the focus on searching for life on Mars has been driven largely by the fact that Mars is kind of Earth-like in a lot of ways. Earth-like meaning in many ways familiar to you and me. But where the search for life in the solar system is going is not now to Mars so much, or at least it's expanding beyond just Mars to include the outer solar system, and not the planets, not Jupiter, not Saturn, not Uranus, not Neptune. Searching for life on those worlds is not something that we're doing. But we are increasingly fascinated by the prospect of life in the oceans that lie beneath the icy crusts of the moons of some of these planets. So Europa in particular looms large, not just in this photograph, but in our thinking about how we're going to explore for life in the solar system. So Europa is a moon of Jupiter that has an icy surface, but beneath that icy surface is a liquid water ocean. It's cold, it's dark, it's probably salty, but we know that it is, if it is what we think it is, and we haven't actually seen it, we haven't been able to get in there and touch it, but we're pretty sure it's there from a bunch of indirect lines of evidence. We're pretty sure that it is an environment that could be hospitable to microbes that actually live on Earth today, if we could get them there. Not that we want to do that, but the point is it's a habitable environment. Even all the way out to Pluto. So probably most of you have seen these spectacular images of Pluto that came from the New Horizons spacecraft in the past year. This turns out to be a fantastically complicated surface. It's fantastically complicated because it's geologically active. But it's not rocks that are moving around, it's ices. Ices of methane and water and all sorts of other things. And for all this geological activity to be happening to make this very complex surface with freshly erupted stuff on the surface, it's very likely that there's here, even on Pluto, right, the furthest non-planet, I guess, I still say it's a planet, the furthest planet out, there is probably a liquid water ocean beneath that icy crust. It's probably a mixture of water and ammonia to lower the freezing point so it can stay liquid, but it's probably also a habitable environment out there. But the one that gets me the most excited, and a lot of people the most excited, is in this picture. This is Saturn. It's not Saturn that gets us excited, and it's not this guy here. This is one of Saturn's moons. What gets us excited is this guy here, which is another of Saturn's moons, a little guy called Enceladus. You probably can't even see it in the back. There's the arrow. This little moon here that's close in. And the Cassini spacecraft, in its exploration of Saturn, discovered this amazing thing that nobody expected, nobody predicted, and until recently has been hard to explain, and still is hard to explain. It's discovered these jets of water spewing out from the south pole of Enceladus. And these jets, almost certainly, there's been argument about this, but the consensus now is these jets indeed are jets of water that is percolating up through cracks in a thick ice crust, coming from an ocean that we now think is global, an ocean layer that is global beneath that icy crust and above a rocky interior. And where you have water and you have rock, and if you have some heat inside to generate chemical reactions between the water and the rock, you have conditions very similar to those at the bottom of the Earth's oceans. Cold, dark, salty, but heated and full of all sorts of elements that leach out of rocks and can drive all sorts of interesting chemistry, including potentially chemistry that leads to life. So we're tremendously excited by this discovery, but there's more. So the Cassini spacecraft has flown through these plumes a few times to make measurements of what's actually in those plumes. I should get out of the way so you can see it. And the goal has been to see, is this a habitable world? So what's in here? Well, there's water. I already said these are water jets, so there's water vapor. There's obviously energy to generate these in the first place. We can infer, and this is a remarkable thing, from silica nanocrystals that are observed in what comes out of these plumes, we can infer that there must be interactions between water and rock at the bottom of that ocean to generate dissolved silica that makes these nanocrystals. It's absolutely remarkable. So we know, actually, from the measurements that have been made by Cassini that there's water-rock interactions at the bottom of that ocean, even though he hasn't gotten anywhere down to even touching the surface. We can infer it. There's reduced, and I say water-rock interactions mean that there's elements like phosphorus and calcium and all sorts of elements that we know are powerfully useful in biology because they're in rocks and they have been leached out into that ocean almost certainly, and we can predict that. We've detected reduced nitrogen in the form of ammonia and other nitrogen-hydrogen compounds. That's vital for biology as we know it. And the kicker is that we have detected organic molecules, big ones, in those plumes. We don't know what they are. The instruments on Cassini are not good enough to be able to tell us much about them other than that there are large molecules. But that's tremendously exciting. Right? It's so exciting that you look at all this and you say, is this a habitable world? Yeah. Like Europa, there are microbes living on Earth today that could probably eke out a living in this kind of environment. But unlike Europa, here the samples, the material is spewing out for us to sample it. It's like the universe saying, here, come get me, let's see what's here. It's really a stunning, stunning discovery. So there are a couple of missions that some of us here at ASU, me and as well as others, are involved in to try to follow up on these observations. So one of them is a mission called the Enceladus Life Finder, or ELF. Don't blame me for the acronym. I actually don't like the acronym, but it's at least a little catchy. So the ELF mission is led by John Lenine at Cornell, and this is a mission that would basically, a dedicated mission that would fly through the plumes, but with an updated package of instruments, 20 years newer than what Cassini had, 30 years, depends on when it actually happens and launches, that could do things like actually tell what are the organic molecules there. And the goal would be to actually determine whether the molecules that you have there are indicative of biology. So that's a mission that's being conceptualized now and has been proposed once to NASA and shot down and will be proposed again in another year. There's another mission that I think is even more exciting. This is still in the conceptual phases. This is called Life Investigations for Enceladus. And the idea here is to fly through the plumes again, and I'm sorry about the lighting here, you probably can't see this. These are samplers here. So the idea is to collect the material, fold it back into the spacecraft, and bring the spacecraft back to Earth so that we can use terrestrial laboratories to analyze the heck out of the material that's captured. We can do a lot more in a laboratory on Earth than we can in an in situ investigation in a spacecraft. And so the idea is to bring samples back and see if there's anything biological there. So a lot of us hope that eventually we can convince NASA to fund that guy. That's going to be a long mission. It would fund my retirement. We've actually recruited some young graduate students to be part of this planning process with the hope that some of them will end up being the leaders of this thing in 30 years. We'll see what happens. What's really cool in particular about thinking about these icy worlds as opposed to Mars is that if we're really interested in life, the ubiquity of life in the universe, what we really are looking for is not just whether there happens to be life on Mars. We really want, or anywhere else, we really want to know if there's life that has originated separately from life here. A second genesis is the way that my colleague Chris McKay refers to this. And why is that? Well, if life arose twice in our solar system, we can go somewhere and convince ourselves that life arose separately there compared to here, then the odds of life being common go up astronomically, pun intended. Right? If one solar system had life originate twice, then it's got to be a pretty darn easy thing to have happen. Right? And the problem with Mars is close enough to Earth that we exchange material. We have Martian meteorites on Earth. We have Martian meteorites in this building upstairs in the Meteorite Center. And there are almost certainly Earth meteorites sitting on Mars. And we can make a pretty convincing case that microbes in sporulated forms can actually survive the transit. It's at least it's a non-zero hypothesis. And so if we find life on Mars, the first thing we'll be asking is it indigenous? Is it a second genesis or not? On Europa or Enceladus, those worlds do not exchange material with Earth. And so if we found something indicative of biology on Enceladus, we would pretty quickly be able to conclude that it is a second origin of life. So that's fascinating and powerfully interesting. So that's one way that the study of the Earth has informed what we do out there. It's by discovering the extremes in which life can live on Earth, by microbiologists and geologists roaming around this planet, that we've transformed where we're looking and what we're looking for elsewhere. We aren't just looking at Mars, and we aren't just fascinated by canals. We're thinking about more extreme environments that turn out to be really, really fascinating. So let's go through another example of how Earth science informs the search for life beyond. And it's going to take us a bit of, we're going to go a little elliptically before we get to the Earth. We're going to first actually look outside our solar system. We're going to look outside our solar system and think about the planets that are being discovered now at a record-breaking pace by the Kepler Space Telescope and other planet detection approaches. This is the Kepler Space Telescope. It discovers planets by looking for the slight dip in brightness of stars that it looks at when the planet transits across the face of the star. This is a very, very hard measurement to make, but Kepler's been making them astoundingly. We now know there are now 5,662 discoveries of exoplanets, of planets orbiting other stars. 1,963 of those are confirmed, meaning there have been follow-up observations that give us very high confidence that those discoveries really are what we think they are. And there's efforts to confirm the others as well. And this number, every time you give one of these talks, you got to check this because this number updates pretty much daily, and certainly weekly, and very much monthly. So another frontier of the search for life beyond Earth is not just the outer solar system, but also thinking about all these thousands of planets outside our solar system, some of which are Earth-like in some ways. Those are harder to find, but we're starting to find them. Planets that are about Earth size and roughly Earth's distance from their star, if it's a sun-like star, so could have habitable conditions at the surface. So as we look at those Earth-like exoplanets, as we discover them, we start to ask, well, how are we going to look for life on those worlds? It's all well and good to know there's a planet there, but if our goal is looking for life, how are we going to characterize it on a planet that is hundreds of light years away? Oops. So the main way that we think about doing that is by looking for indirect evidence of biology. We're not going to build telescopes anytime soon that can tell us if there's forests on any of these planets. But we may be able to build telescopes that can tell us if there's oxygen, the molecular oxygen, O2, in their atmospheres. And the way that works is as follows. It turns out that the O2 molecule absorbs light of certain wavelengths very strongly. And we've done this experiment in our solar system, essentially. Here's Earth, here's Venus, here's Mars. And what you're seeing here are infrared spectra of these different planets, of their atmospheres. And you can see on Venus here, you see this very big feature. This is an absorption feature. A lot of the light here is being absorbed, and that's due to carbon dioxide in Venus's atmosphere. Venus has an atmosphere that's about 90 times thicker than Earth's, and it's almost all carbon dioxide. It's part of the reason Venus is so hot at its surface. So big CO2 feature. Here on Mars, you also see a big carbon dioxide feature. Mars has a very thin atmosphere, whereas Venus is 90 times Earth's atmospheric pressure. Mars is 6,000ths. It's basically a vacuum by our common everyday standards, but that gas that's there is almost all CO2. So actually, in terms of spectra, it looks a lot like Venus. Now you do the same experiment with Earth. You look at Earth. So you also see the CO2 feature, because we do have CO2 in our atmosphere. It's a much noisier feature because on Earth, CO2 is a trace gas in our atmosphere. It's only about 400 ppm. It's rising, but it's rising slowly and it's very low level compared to Venus or Mars in terms of percent. But what we also see here on Earth is we see this thing here. This is a very strong feature due to the molecule ozone, which is a very rare molecule in Earth's atmosphere, but it absorbs light of this wavelength really, really intensely. So you don't need much of it to detect it. And ozone is a byproduct of having an oxygen-rich atmosphere. So if we could take data like this, we could build a telescope big enough to get this sort of data from the atmosphere of a planet orbiting another star, and we saw something that looked like this, low CO2, CO2 is there, but it's relatively low, and a big ozone feature, we'd start to get pretty excited, because that's a world that probably has a lot of oxygen in its atmosphere. And the best way we know to build up a lot of oxygen in a planetary atmosphere is to have biology there, producing it by photosynthesis. So this is the strategy that we adopt. But hold on a second, there's a question that you might ask right away. All well and good that that's what happens on Earth today, but the Earth has been around for a long time, and the planets we find out there may or may not look like the Earth today. So one of the things we want to know is, well, what's the history of O2 on Earth? Has Earth always had an oxygen-rich atmosphere? Is it a very recent phenomenon for oxygen to build up in the atmosphere? What's the story here? And so as geologists, we then look to the rock record, the ancient record, and we have to go deeper in time than the Grand Canyon, which only goes back about 1 billion years, 1.5 billion years. We need to go back further in time to look and figure out what's the history of oxygen on this world, and figure out if that tells us something, and as you'll see, it does, important about that should inform the search for life beyond Earth. So this is something that I do in my lab quite a lot. My research focuses a lot on grabbing rocks from ancient Earth and trying to tease out information from them about what the environment was like in the past, and especially the presence of oxygen. So we look at rocks like this. These are black shales. This happens to be what came out of a drill core. Here's a drilling operation here where they're basically drilling I think it should say here, there should be a scale here. No, the scale went away. This is about 2 inches across here, sliced in half. These beautiful gold laminations are laminations that they're of fool's gold. It's pyrite, iron sulfide. That's not what we're interested in so much. We're interested in the chemical makeup of the black stuff here. And these rocks are 2.5 billion years old. And so what we've been doing is digging into these rocks and other rocks like them to try to figure out if we can find chemical traces that are indicators of the presence of oxygen in the environment. And we do that using big, sophisticated instruments, fancy laboratories that we have here at ASU in CC, and well-trained graduate students who work crazy long hours to do the hard work that it takes actually to take these rocks and powder them and dissolve them and make measurements, painstaking measurements on these kind of instruments, these mass spectrometers, to figure out what's there. We do things like We do things like look for the abundance of elements like molybdenum and rhenium, elements you probably don't think about too much in your daily life. Molybdenum is a fun element, though. It's element number 42 in the periodic table. If any of you are Hitchhiker's Guide to the Galaxy fans, you know that 42, this is a very important number, right? It's the answer, right? Right, so this is like the most important element on the periodic table, whether you know it or not. We care about it as geochemists because its chemistry in the environment is very sensitive to whether or not there's oxygen. When there's not a lot of oxygen, it doesn't move around much. When there is oxygen around, molybdenum gets around. It dissolves in the water, it accumulates in seawater, and so its chemistry in the environment is very different, and so it can be used as an indicator of whether or not there was oxygen in the environment in the right kind of rocks. So in the kind of rocks that I just showed you, this is what we call a stratigraphic column, the geologists call. So this is a cartoon of a core of rocks that stretches for about 100 meters. And what we did is looked at the amount of molybdenum in these rocks. We did a whole bunch of other things too. This is just the sort of first order thing that we look at. We looked at the amount of molybdenum in these rocks, and we found, to our surprise, when we cracked these guys open, we found enrichments of molybdenum and also of rhenium in these rocks that are quite old. And they're kind of transient. They move around. And so what we've inferred from this and other lines of evidence is that there was probably oxygen around, but in small amounts bouncing around. We referred to it as whiffs of oxygen in the environment at around 2.5 billion years ago. And so we make measurements like this, and colleagues of ours make measurements like this, and we compile this consensus view of what the oxygen story has been over Earth history. So here's a chart. I think this is the last chart I'll show you. This is concentration of oxygen. So higher is more. This is time. So here's 4.5 billion years ago. Here's today. So the data I just showed you a glimpse of is data that tells us that, at least our interpretation, is that around 2.5 billion years ago, and you can find similar evidence back to around 3 billion years ago, there may have been whiffs of oxygen in the environment, small amounts transiently. But shortly after that, around 2.3 billion years ago, there was a sharp rise of oxygen. Not to levels like today, but to levels that may be detectable from space. And then there was another rise to the modern level of about 21%, starting around roughly 500 million years ago. This is referred to as the Great Oxidation Event in the business. So this marks the transition of the Earth from a world where oxygen in the atmosphere was a very rare thing to a world in which it started marching towards what it is today. Probably the biggest transition in the history of the planet, at least before we started doing what we're doing. We may or may not end up rivaling what nature did here. So it's a transition from very little O2 through whiffs to lots of O2. This is the history. So what does that mean for the search for life? Well, a world like this is a world that is inhabited and where that life is detectable because there's enough oxygen that you would have a hope of detecting it. But this world, I'm mishandling my pointer. This world before, where oxygen was very scarce, it was being produced, we think, but it was very scarce, and it was probably inhabited. It was inhabited for sure. It was probably inhabited by organisms making oxygen, but the oxygen was not accumulating into the atmosphere to levels that were detectable. So why is this? Why did this change? Why? So the easy thing you might say is, well, this is when life figured out how to make oxygen. That's what transformed this. But we have this whiff evidence as well as other lines of evidence that suggest to us that no, life was probably already doing that earlier. Something was keeping the oxygen down. And we don't know what that was. We argue about it. We have a lot of ideas, but we don't know. And this is kind of important because we're going to be putting the James Webb Space Telescope and future telescopes in space, and we're going to be figuring out which planets out there are Earth-like maybe, and we're going to be making decisions about whether to point this thing at that planet or that planet or that planet and put the hours and hours and hours of time that it's going to take to tease out the kind of data that I showed you before, the spectral data, that might tell us whether or not there's oxygen in one of those atmospheres. So we would like to know before we spend all that time whether that planet is likely to have oxygen, or that planet is likely to have oxygen, or that planet is likely to have oxygen. And to know that, it would be kind of nice to know what controlled oxygen in Earth's history. So we could maybe have a theory that would allow us to make some predictions about how some other planet might work. So it turns out that geology is profoundly important here. Not only is geology important for teaching us about the oxygen history on Earth, but it turns out that it's geology that probably controls the oxygen in the atmosphere. It's not just the biology. Biology produces it, but what takes it out of the atmosphere over geologic time are reactions of that oxygen molecule with rocks through weathering, with volcanic gases coming out from submarine volcanoes, with gases coming out from volcanoes on land, and weathering reactions in the deep sea. These are all reactions that take oxygen out that all involve that gas, that molecule, which is produced ultimately by biology, being consumed by reactions with stuff that comes from the solid Earth, that comes from the interior ultimately, because where does all this crustal stuff come from? It comes from melting of the Earth's interior when it erupts to the surface and giving us crustal rocks. And that interior, that stuff that's coming up, is chemically very reactive with oxygen. And that's what most of the planet is, right? So the oxygen that we breathe and that we're interested in detecting elsewhere is a very, very thin veneer on top of a planet whose interior is essentially an infinite sink for oxygen. So what matters, what probably controls how oxygen accumulates in an atmosphere is the rate at which the stuff happening at the surface interacts with all this stuff. The rate of volcanoes, the rate of subduction, the rate of the dynamics of the solid planet is probably what in a profound way controls whether a planet can accumulate oxygen or not. So you may have Earth-like planets that will never accumulate oxygen because they may have, for various reasons that we could go into later, they may have more vigorous interactions between the surface and the interior. And that's a set of concepts that we barely understand. We've only just started thinking about that as we start thinking about these extrasolar planets, these exoplanets. So this is something else we're doing here at ASU. So this is a project that I lead I'm the PI of, the Dynamics of Earth System Oxygenation. It's a project funded by the National Science Foundation, $5 million funding ASU as well as 4 partner institutions, MIT, Riverside, Maryland, and University of Washington. There's 19 scientists and a whole bevy of students involved in this. And the goal of this project is to build a bridge between those of us like me who study the history of the Earth's surface environment and those like Professor Taberzi over there who study the interior of the planet and how it works. Right? So you may think, well, you're all geologists, don't you guys talk to each other all the time? But it turns out, yeah, we talk to each other over coffee and at faculty meetings, but our research actually rarely intersects. And those of us who study the history of Earth's environment rarely think too much about what's down there and how it interacts with the surface. And it turns out that those who study the physics and chemistry of the Earth's interior rarely think about this oxygen history question and what it has to do with exoplanets. And so NSF has given us funding to try to actually drive that conversation and produce some cool research results. And we have cool results that I don't have time to talk to you about, but we'd be happy to chat about later, that are starting to change the way we think about this. So I hope you've gotten a sense here of how Earth science informs our search for life beyond Earth. And I want to leave you with one other quick example that may torque the way we're thinking about this. It's a very simple set of observations, but that are worth keeping in mind when we're thinking about the search for life. So I've already shown you a little bit of the history of life and environment on Earth. 4.5 billion years ago, or 4.6 billion years ago, it's 4.56, so it depends how you want to do this. I should round to 4.6 here, is where we begin. Earliest signs of life, around 3.8. Whiffs of oxygen, around 2.5. Lots of oxygen, around 2.3. When do we start having things like animals? Things that you could walk up to and say, oh, there's something there. Because I didn't really talk about this, but what's producing this oxygen is bacteria. It's microbes. It's not plants. Plants come really late. So the oldest fossil animals, that we think they're animals, are things like this. This is a fossil, what's called Dickinsonia, part of what's called the Ediacara fauna. And you find these, this is the oldest, this is an example of the oldest macroscopic metazoans. Anybody have a guess when these appear? The youngest person. A little older than that. We can do this whole guessing game here if we want, but we should do like Price is Right, No, you're over. Getting closer. Yeah, that's about right. So about 0.6 billion years ago, about 600 million years ago is where these first appear. Notice how far up the time scale we are here, right? We're getting pretty close to today. Many of you may have seen geologic timescales that don't look quite like this, because usually what geologists do is they play a trick on you. They plot all the young stuff as most of the geologic time, because we have lots of rocks that are young. And all this old stuff, which is most of Earth history, gets compressed into a few little boxes at the bottom of the time scale. And it gives you a totally false view of geologic history. Most of geologic time we don't have a lot of material from, but this is most of it. And then the first animals appear here. And then let's pick out something else. How about dinosaurs, right? When did dinosaurs go extinct? Somebody knows the answer in the audience here. Oh, good answer. Good answer. All right. Here, give him the mic. He can drop the mic and just walk out of here. Okay. When did these guys kind of go away? Not the birds, but the big guys. So it's about 65 million years ago. That is, if you just put it on this linear time scale, I mean, it's actually like overlapping literally with the word today, right? Right? I mean, it's like yesterday, geologically speaking. So you normally think about dinosaurs, that's a long time ago. It's really not. And then you go to, first hominids, right? Us, our ancestors. So we're like, right on top of here. It's not even yesterday. It's a few hours ago, geologically speaking. So what does this tell us that's relevant to the search for life beyond Earth? Well, life gets going quickly. We said that earlier. And it persists pretty tenaciously. We haven't talked about this, but the Earth goes through lots of drama over all this time. Lots of things happen. And life keeps finding a way. And it evolves and transforms and gets more complex. And that's a fascinating story we don't really understand either. But it keeps on ticking. But tool-using intelligence, us, stuff like us, doesn't emerge until very late, if at all. elsewhere. We don't know, right? It's very late. And what this might tell you is that it's easy to get life going, but it's really hard and maybe very rare, maybe a very unlikely thing for tool-using intelligence, technological intelligence, to evolve. Maybe it's so rare that maybe we're the only ones. We don't know. We don't know what set of coincidences and chance needs to happen for us to emerge. We don't even really know, and geologically speaking, if the development of intelligence and tools is actually evolutionarily advantageous. It seems to be right now. We can certainly do all sorts of stuff that seems to enhance our survival, but over the sweep of tens and hundreds of millions of years, we don't really have much of a clue except our guesswork. So we come back to this image and ask, are we alone? Kind of depends on what you mean by we. If you mean microbes, if you mean is there life elsewhere, my bet would be, yeah, it's probably all over the place. I bet that the emergence of life is pretty easy if you have the right conditions, and I bet the right conditions are common. So maybe life is common, but I would bet you that intelligent life is pretty rare. And that maybe it's just us. If when you say, are we alone, we're asking about beings like us in some way. It may be that we are alone. Now, Arthur C. Clarke, famous science fiction writer, postulated this, and he has this famous saying that I kind of like, but I kind of don't like. Two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying, he said. I don't see it that way at all, actually. I think they're both actually tremendously inspiring. So if life is ubiquitous everywhere, that means that we're going to have to be really, if intelligent life is ubiquitous, it means we have to really screw things up, right? If we have lots of older cousins out there, maybe they're not biologically related, but others who have gone through what we've gone through, then that's tremendously inspiring. If we're alone, you may think at first, oh wow, that's depressing, right? The whole Holy Grail thing. But let me submit to you this. Let's say we really are alone. Let's say we're the only intelligent beings anywhere in the universe. In 100 billion stars in our galaxy and 100 billion galaxies out there, let's say we're the only ones. Well, that means that the future of life in the universe as intelligent life, the future of the consciousness of the universe, depends on what we do here, now, and in the future. I find that tremendously inspiring in its own way. It's a different sort of thing, but it's tremendously powerful to think about that. That the future of what happens with life in the universe may depend in all sorts of powerful ways on what we do here. And so I'd like to leave you with that thought, that whichever answer it is, whatever the science of astrobiology tells us, is tremendously inspiring and should motivate us in the search. Thank you.
Got time for questions, but I think someone has to carry the microphone because there's this is being broadcast. So go ahead, some questions.
I can pick them out. Uh-oh, I can't even see him.
First of all, thank you very much for a very inspiring and interesting presentation. I had a question on a matter of time. You speak of 60 million or 60 billion years ago, but yet carbon dating is only accurate to about 60,000 years. How do they come about with the figure of 60 billion years?
Right. So I had 4.5 billion years, I think was the oldest thing I did. But I understand the question, right? So carbon dating only goes back so far. How do we get these older ages? So there are other radioactive clocks that we can use other than carbon. Carbon was the first one that, well, actually it wasn't the first one. It's kind of an easy one to work with in certain ways. But uranium decays to lead, and that is another clock that's very useful. Rhenium decays to, or osmium decays to, rhenium decays to osmium, sorry, now I'm getting myself confused. Rubidium decays to strontium. There are a number of these clocks that play out over much longer timescales that then can be used to get ages. And what's remarkable is that there's enough of these that overlap that we can actually take certain kinds of rocks and date them with more than one of these clocks, and they give us very consistent results. And so one of the things certainly the geologists, geochemists, especially those of us who actually are masters or purport to be masters of this art, are pretty convinced of is the geologic timescale. It's one of the most transformational things that we've discovered in the last 100 years, we've figured out in the last 100 years, is to be able to precisely date the sequence of events on this planet, as well as the sequence of events in the early stages of the solar system's formation. It's as transformational as the discovery of DNA, I would say, actually, in terms of our understanding of our place in the cosmos, but it doesn't get quite the same hype.
Okay. I have a question about that intelligence, because you see here on Earth, dogs are intelligent. We promoted their intelligence from wolves. We evolved them quicker. But in the ocean, you have mammals, whales, dolphins, that can understand English languages. We've taught them.
Right.
You look in the volcanic vents in the bottom of the ocean, you have life evolving. There's so many different kinds of life.
Mm-hmm.
It's hard for me to believe that there would be, a limited amount of intelligent life.
Right. So first of all, I made a point of, I didn't say intelligence just, I said technological or tool-using intelligence. So whales are great, but they don't have opposable thumbs. And they don't build radio telescopes, and they don't build rockets. And so...
Give them time.
But I think, the point is well taken. We don't know. And I'm giving you my opinion based on the geologic history, that it seems to have been taken quite a long time to get to whales even, right? Whales don't appear that much earlier, really, than we do in the kind of time scale I was showing you. It seems that the evolution of big brains of any sort is not something that happens early. Evolution of animals is not something that happens early. And that may be telling us something about the probability of that happening, and that it may be a rare thing. But we don't know. The problem is right now it is a realm of belief. You use the word belief, I'm giving you my opinion. Great, we could argue over beer, we should do that later. But really what we need to do is get data to be able to figure that out, and that's what I'm trying to say. And I'm trying to say whatever the data show, I think it's going to be fascinating, and it's something that should inspire us in the search. Want me to pick? Young people in the front. Oh, okay, whatever.
Very quick question. I was wondering, do we know of any organisms that do not require liquid water?
No. Easy.
I see.
We don't. So we don't. On Earth, all life needs liquid water. Any life as we know it will even hypothetically need a solvent, because you need to move stuff around. You need to move nutrients in and waste out, and the simplest way to do that is with chemistry in solution. On Earth, water is ubiquitous, and so it's the most natural choice of solvent. It's hard to really actually imagine places on Earth where it would make sense to evolve something else. Now, on other worlds, you can imagine other things. On Europa or Enceladus, water still makes sense. Water is really common out there. On Titan, which is Saturn's really big moon, which has ethane oceans, it might make a heck of a lot of sense evolutionarily for chemistry that is based not on water chemistry, but on organic liquid chemistry to sort of give rise to biology and be the basis of biology. The problem is we quickly get into the realm of science fiction. We have no idea how that would work. And so there's a lot of interest in trying to explore Titan for biology, but we actually don't even know what we'd be looking for exactly and how we'd look for it. Probably you would just start looking for weird shapes in the water and hope that might lead you somewhere. But it's a much harder thing to do than to look for chemical signatures that can be detected in certain ways more easily. So that's the longer answer. So no, but the longer answer is there. Want me to pick? All right.
It looks like once you get the oxygen concentration up to 21%, intelligent life develops pretty quickly.
Well, so that's an interesting connection. So animals, for a bunch of reasons, even the simplest animals that I showed you, need high levels of oxygen. We metabolize, we use a lot of energy, and the best form of energy is, for a biological standpoint, is to react organic molecules with O2. That's get the best bang for your buck. And so there certainly is a connection there, that as oxygen rises, you make possible for these other things to happen. No argument. So you could make the case, and it's interesting, I haven't actually seen anybody make this case in the literature, but somebody probably has, that if you found a world with a lot of oxygen, right, that you could make a logical argument that not only is there biology there, but there's probably complex organisms there, because at least from Earth history, exactly what you said is correct. Complex life seems to evolve pretty quickly. But how complex does it get, and how easily does that happen? The jury is out. We don't know.
What was the geology that changed that from being like 8% up to 21%?
We don't really know. That's another puzzle. So there's two. You saw two steps. That second step is actually more mysterious than the first step. Mysterious not in some supernatural sense, but just we haven't really quite figured it out. There are a lot of ideas, and we aren't quite sure. That first rise, the great oxidation event, we've known about for a long time, so we've chewed on it for a long time. There are a lot of interesting theories to play with. That later one, really the last decade, last 10, 15 years have been a lot of work to convince ourselves there really was a rise and to try to figure out the timing of it. And we really haven't gotten into that second stage as deeply of really trying to understand why it happened. We've been figuring out what happened for the most part for that second rise. In fact, it's kind of interesting. For a long time, it was the fossil evidence, it was the rise of complex organisms that was the strongest evidence that oxygen must have increased. And people then would also say, well, it's because you have oxygen around, more oxygen, you can have complex organisms. So it was this kind of circular argument. But now we've developed independent evidence of the oxygen.
One last question.
Sure. And I'll be happy to stay up here and take questions after people are gone. Invaded something burning. No.
It was It was practically answered in your answer to the previous question. That's why I gave the microphone back. But I was just going to ask, how could you resist not telling us something about what was thought of for that great oxygen event? It's so striking.
Oh, well, because it would be another 10 minutes of talk.
Yeah, I figured that.
All right, well, let's give Ariel another great hand for an inspiring talk. Woo! So just a couple of final tidbits here. So you want to keep up with us on social media if you're into that. One thing you can do is figure out where to find this video recorded. So it's we were live streaming it tonight on ustream.tv/ASUTV. So you could find it if you want other people to
edit out all the
share
problems. Edit out all the mistakes.
Yeah. No, I think it was all great. So thanks for attending. In the fall, the first one will be Dr. Dave Williams will be talking on August 25th, and I think he'll be talking about one of those small planets that Ariel was talking about, the Ceres and Vesta, two great asteroids. Make sure to get some of our flyers. We've got some really great documents out there. I just want to wave it here. So get one of those, and it has lots of information about CC, and also opportunities for giving opportunities, some information to how to support CC. And so thanks a lot for coming tonight, and good night.